Hello, this is Paul from Tech. In this video, let's prove Theorem 4.6.5, basis of a finite dimensional vector space. We have two conclusions. So, all talking about the finite dimensional space. So, say S is a set of vectors. A says if S span V, but it is not a basis. Okay, therefore we can shrink, or reduce S into a basis. So we can find A simply by minus theorem we learned. So for B, if S is linearly independent but is not yet a base, so we can grow S into a basis. We can get the result simply by plus theorem. Okay, so let's see what. So this is finite dimensional vector space. So I can take example. Let the dimension, let's say, the dimension of the vector space is simply 3. It's a 3 dimension. Okay, if it's a 4 dimension or 5 dimension is the same. Okay, so you can do. And the S. So let's say S span V, but is not basis. So now, if S span V is not a basis, with first step, so we need to say we have more than 3 vectors in S. Therefore, we can reduce S into a basis. Okay, let's say Y. So first, we say the number in S, is greater than 3. Otherwise, if it's not greater than 3, then the number should be 3 or less than 3. If the number is 3, it's contradict with the theorem we learned before. Because if it's a 3 vector and the span is V and this S should be a basis, right? If the number of vector in S is less than 3, also contradict. Why? Because we have a theorem before, says if the number in S is less than the dimension, so the span should be not the whole space. Okay, let me write. Okay, because the number in S is greater than 3, so we can simply say the number is 4. And you also can do the same. The number is 5 or more than 5. The same way to prove. So let's say, so we have 4 vectors inside. 4 vector is more than 3, right? So it's more than the dimension. And we need to say at least one, one vector can be another linear combination. Then therefore we can reduce. So how do we reduce? And the first we need to know is linearly independent, right? So we say linearly dependent. Why is linearly dependent? We have a theorem before, so which is 4.6. So by the theorem 4.6.2 before, we say if the vector number is the number of the vector is more than the dimension, this should be linearly dependent, right? Okay, so that's the first. Linearly dependent means that at least one vector is a linear combination of the other. So let's say V4 is a linear combination of the others. Now, so we can remove V4 from the set of S so that we still have the same span because we have a theorem. Okay, that's the minus theorem already stated, right? So therefore, and this is the minus theorem. And because we have the condition span equals the whole space, right? So this equals V. See, what do we get? And then now we have a set of vector with the 3 vectors. exactly the vector number equals the dimension, and also the span equals the whole space. And then we have another result that in this case, V1, V2, V3 should be a basis, right? So therefore, and this is by the theorem 4.6.5. Okay, so we get the result. The original is more than 3. Now we can remove one vector. So what do we get is a basis already. This is A. So let's look at how to say B. Very similar. Okay, so we do for B. How to grow a set of vectors so that we can find a basis. The same, we still look at the dimension is 4. Okay, the dimension is 3. We need to give a set of vector linearly independent, but it's not a basis. Okay, so this is S. S is linearly independent, but not a basis. First, we need to see the number of vector in S is fewer than 3, and then we can grow S into a basis, okay, by the plus theorem. So how to say S has a number less than 3? Okay, we can think about this. Okay, if S is equal to 3, it's impossible. If S equals 3, should be a base. If S is greater than 3, should be linearly dependent, so contradict. So therefore, this is true. So otherwise, contradict with the previous other results. And then we look at it, because the number of the vector in S is less than 3. So let's simply say we have 2 vector inside. You also can say we have a 1 vector, okay, whatever. It's the same proof. And now we can grow, okay, so this S, so that we can find a basis. If you only have 1 vector, you can grow twice, so you still get a basis. The same idea. How to grow? We have a plus theorem, right? So how to plus? So we need to find a vector is not in S, but in V, which means we need to find a vector does not belong to the span of S, so we can grow. Otherwise, we cannot grow. Is that true? Yeah, definitely. So now, okay. So by the theorem 4.6.2b, so we say now S, the span of S should be not equal to the whole space, because the whole space has a dimension 3. Now S, we only have 2 vector, and the number of vector is less than 3, so the span should be not equal to the whole space. Okay, in this way, this means the span is a subset of V, but does not equal V. Okay, it's a proper subset. Because the span is a subset of V, therefore we should find them. Is this true? Because the span is a subset, therefore we can find a vector in the whole space, but that vector does not belong to the span. Okay, is not belong to the span, therefore by the plus theorem, so we can add this with 3. See, we can get it. V1, V2, V3. Okay, by insert V3 into the original S, and what we get is they are linearly independent. And now we already get what we need. We need a basis. V1, V2, V3 should be a basis now. Okay, because the dimension is 3, and then here we have 3 vectors and also linearly independent. Okay, and before we have this theorem. So by the theorem 4.6.4, so V1, V2, V3 is a basis. So now we definitely grow into a basis, right? And that's the proof. Thank you.